Today's lesson from Unit 1.1 is an introduction to writing proofs. We use geometric proofs to show how given information, whether it's from a diagram or another source, leads to a logical conclusion. And we do a proof through a series of statements and reasons. So in other words, everything we say has to be justified, or we have to have information to back it up. Before we get into writing our first proof, let's talk about the components of a proof. Now, proofs can be made up of 5 different parts, but they may not contain all 5 of these parts. For example, the first part is a statement of a theorem. Now, we would see this in a case when we were trying to prove a particular theorem. So theorem. The second piece is a diagram to illustrate our given information. We know how valuable diagrams are to solving problems in geometry. So very often diagrams are used to show how our given information is used to lead us to our conclusion. The third component of a proof is a list of that given information. Okay, and that list might include one piece of information, might include 2, might include 3. But then we have to figure out how to use that given information. The fourth item is a list of what you are to prove. Now, for most of our proofs, we'll just have one thing that we're trying to prove, but every once in a while we get a proof where we have to prove more than one thing is true. And finally, what the proof actually is, the biggest part of the proof is a series of steps, or we should say a series of statements and reasons that lead from the given information to what you are trying to prove. So number 5, most important part of a proof. All right? And very often that's the most challenging part to do. When we're writing a proof, we want to have handy a list of our definitions, postulates, theorems, and properties from algebra, because we're going to use those as our reasons in our proofs. So if you have any of those worksheets handy, you may want to take them out as you go through and try these examples. In our first example, we have this algebraic equation that we're going to solve, but we're going to solve it in 2-column form. So in the left-hand column, go our statements, and the right-hand column is for our reasons. So all of the work in solving the equation has to stay on the left side, and then we're going to support our work with a property from algebra, or a property from geometry, or a theorem, or a definition on the right-hand side. So to start with, we've got this equation, 3x minus 1 divided by 4 is equal to 5. And we know that equation because it was given to us. I gave that to you, so now we have to solve it. So think about how you would actually solve it. Since I see 3x minus 1 is being divided by 4, I know that I want to do the opposite, or multiply both sides of this equation by 4. So on this side I would multiply by 4 over 1, and on this side I multiply by positive 4. So these 4's will divide out. 4 divided by 4 is 1, and that's going to leave us with 3x minus 1. And on the right-hand side, 5 times 4 is 20. So when we're thinking about giving a reason to justify what we just did, since I multiplied both sides of the equation by 4, that's an example of the multiplication property of equality. Okay, for our next step, keep thinking along the lines of algebra and what you would do to solve this equation. I know I want to isolate the variable, so to isolate the variable in this case, I would add 1 to both sides of the equation. Now, we know that we have to keep things in balance when we're solving the equation, so whatever we do to the left side of the equation, we do the same thing to the right, and that's an example of the addition property of equality. And again, you can find all of these on your list of algebraic properties. Finally, to finish solving our equation, 3x equals 21. To isolate x, we need to divide both sides by 3. So we end up with x, because 3 divided by 3 is 1. 21 divided by 3, we've solved the equation. And we'll finish off our proof by saying that we use the division property of equality. Typically, students find algebraic proofs a little bit easier when they're just getting started with learning how to write proofs. But I just have to tell you that geometric proofs only get easier with practice. So let's take a look at our next example. In our second example, we're given that line segment RS, which is this little segment right here, is equal in measure to line segment PS. We're also told that line segment ST is equal in length to line segment SQ. So it's not a bad idea to, when you first read your given information, to mark it in the diagram. And we're asked to prove that line segment RT, that whole line segment from R through S to T, is equal in length to line segment PQ. Now it seems like it's pretty logical. We should be able to prove that, but let's take a look. So first thing, set up your two columns. Again, statements on the left and reasons on the right. In our first statement, we're going to go ahead and say that RS is equal to PS. And we're also going to go ahead and say that ST is equal to SQ, and that's given. Now, after seeing a few proofs, you'll know when you need to keep the given information together on the first line, or when you need to separate your pieces of given information. We don't always put all the given together in line 1. If you take a look in step 1, if I just put a little plus sign here, imagine if we were to add RS plus ST, we could then say that that's equal to PS plus SQ, because this is an example of the addition property of equality. Because we have equal amounts here, and we're adding them to two equal items here. So RS plus ST is indeed equal to PS plus SQ. And you can take a look on your sheet of algebraic properties and you'll see something similar that says if A is equal to B and C is equal to D, then A plus C is equal to B plus D. And that's exactly what's happening here. In our third step, we need to introduce line segment RT and line segment PQ. So what we're going to do is use segment addition to say that line segment RT is made up of the sum of RS plus ST. And we're going to introduce line segment PQ, the length of it, by saying that PQ is equal in length to the sum of PS and SQ. And again, that's segment addition. So I'm going to say segment addition postulate. Okay, we're ready to write our final step for our proof. If you take a look right here, we said RS plus ST, and we also set it down here. Since RS plus ST is equal to RT, we're allowed to take out RS plus ST in this equation and replace it with RT. You're replacing it with something that's equal to it. On the right-hand side, we have PS plus SQ. Down here, we also have PS plus SQ. Remember that was equal to PQ. So we're going to take out that PS plus SQ and replace it with PQ. So when I think about taking something out and replacing it with something else, that's a way to help me remember that that is the substitution property. Okay, we've achieved our goal. Our goal was to prove that line segment RT is equal in measure to line segment PQ. If you check out your proof statement, it's a match. In our third example, we're given that the measure of angle AOC, which is this large angle right here, is equal to the measure of angle BOD, this large angle right here. And we're asked to somehow prove that angle 1 is congruent to angle 3, or the measure of angle 1 equals the measure of angle 3. Well, what I notice about these big angles, angles AOC and BOD, is that they overlap here in the center. They both have angle 2 in common. Right? So if we could just subtract out the measure of angle BOC, or in other words, the measure of angle 2, then that would leave us with the measure of angle 1 being equal to the measure of angle 3. So here's how we're going to achieve that. So set up your two columns. So left-hand side is for our statements. I'm going to take a shortcut and just write S. And this is R. Check with your teacher to see if you're allowed to do that. On the left-hand side, start with your given information that the measure of angle AOC is equal to the measure of angle BOD. And that, of course, was given. In step 2, let's say what the measure of angle AOC is made up of. Measure of angle AOC is formed by adding the measure of angle 1 plus the measure of angle 2. And we're going to do the same thing for the measure of angle AOD, or BOD, and say that the measure of angle BOD is equal to the measure of angle 2 plus the measure of angle 3. We can put those two together because the reason for that to be true is that those two are examples of the angle addition postulate. Just because you're adding angles together doesn't necessarily mean it's the angle addition postulate, but in this case it is, because angle 1 and angle 2 are adjacent and they form that larger angle of angle AOC. Same thing with angle 2 and angle 3. They are adjacent and they do add up to and form angle BOD. In step 3, we're going to use a little bit of substitution. So check this out. The measure of angle AOC is also equal to the measure of angle 1 plus the measure of angle 2. So take out the measure of angle AOC and replace it with the measure of angle 1 plus the measure of angle 2. On the other side of the equal sign, we have the measure of angle of BOD. We define the measure of angle BOD as being the measure of angle 2 plus the measure of angle 3. So take out the measure of angle BOD and replace it with the measure of angle 2 plus the measure of angle 3. I'll lift out an angle symbol there. Okay, and again, that is substitution. In step 4, we need to be really clear about something that is pretty obvious. Before we can just subtract the measure of angle 2 from both sides to leave angle 1 and angle 3 by themselves, we have to say explicitly that the measure of angle 2 equals the measure of angle 2. Okay, we all know that that's true. An angle is equal in measure to itself, but we need to say that. It's just one of the rules for writing proofs before we can use subtraction. So the measure of angle 2 is equal to the measure of angle 2 by the reflexive property. Again, keep that list of postulates and properties handy so that you can quickly find those reasons. In our final step, go ahead and subtract the measure of angle 2 from both sides and make your conclusion that the measure of angle 1 is equal to the measure of angle 3, and that it would be subtraction property of equality. Okay, good luck on your homework. Remember that proofs only get easier with practice.